Section 2.6 deals with solving compound inequalities. We're starting with a warm-up with 4 problems in which we have inequalities that need to be solved and graphed. Alright, so take a minute to check your solutions, specifically number 2. Number 2 says 23 is less than negative 2x plus 3. So because we only have one variable term, we're just going to isolate it where it is on the right. So that means we need to subtract 3 from both sides, leaving us with 20 is less than negative 2x. To get x completely alone, we must divide both sides by negative 2. And because we divided both sides by a negative, we need to make sure we flip the inequality symbol. But we also need to make sure that we leave everything in its position, meaning the 20 divided by negative 2, leaving us with that negative 10, keeping it on the left, keeping then the x on the right, and then flip the overall problem at the very, very end. Okay, so x is less than negative 10. Okay, so our goals for today are to be able to solve compound inequalities with one variable and graph solution sets of compound inequalities with one variable. So first of all, a compound inequality is 2 simple inequalities combined into one statement by the words and or. An intersection is technically the solutions of a compound inequality involving the word and, whereas the union is the solution set of a compound inequality involving the word or. Okay, so what you're going to find is that ands go in and ors go out. Okay, so the first 2 in this little visual table here, these are both ands. Okay, so we're shading between 2 and 6. So x is greater than 2 and x is less than 6. So x is literally sandwiched between the 2. The second one is just including those endpoints with closed circles. The bottom 2 are or situations where we only need to satisfy one statement or the other, not both. So ors are going to be going out. Okay, so x is less than 2 or x is greater than 6. So it's one or the other. It can't be both. Okay, it's not mathematically possible. Okay, and the or equal to's will also be in play as well. So here's some examples with ands. Number 1 says that the pH level of a popular shampoo is between 6.0 and 6.5 inclusive. Write a compound inequality to show the pH levels of this shampoo and graph the solutions. So it needs to literally be between 6 and 6.5. So let's sandwich it between the 6 and the 6.5. So I'm going to just make it x. And it's going to be a less than sandwich. So it's got to be between 6.0 and 6.5. Now if we kind of read this backwards, 6.0 is less than x would mean x is greater than 6.0. And then x is less than 6.5. So it's saying it needs to be literally between 6.0 and 6.5. And due to the fact that it says inclusive, it means that those endpoints are in fact included. Okay, notice these are less than symbols. Okay, with these ands, they're going to be less thans. It's going to be a less than sandwich. Okay, so our variable, which in this case is the x, which represents the pH value. So let x equal pH level. So there is our compound inequality, and here is our number line. So we'll go 5, 5.5, 6, 0.0, 6.5, 7.0, 7.5. Okay, so we're going to be between 6.0 and 6.5 inclusive. So we need a closed circle on 6.0, closed circle on 6.5, and shade in between. Number 2 says that the free chlorine in a pool should be between 1.0 and 3.0 parts per million inclusive. Write an inequality to show the levels that are within this range and graph the solutions. Okay, so the chlorine level needs to be between 1 and 3. So it's sandwiched between, it's a less than sandwich. 1.0 is the small number of the range. 3.0 is the largest number for our range. And it is inclusive. So we need the or equal to. Okay, so let C equal chlorine. And here's our number line. Okay, so we've got closed circles on 1 and 3. Say less than sandwich, so it needs to be between 1 and 3, so we're shading between the 1 and the 3. So C is bigger than or equal to 1 or less and less than or equal to 3, so between 1 and 3. Okay, so here's a visual representation. It says that in this diagram, oval A represents some integer solutions of x is less than 10, and B represents interval solutions of x is greater than 0. The overlapping region represents numbers that belong in both ovals. These numbers are solutions to both x is less than 10 and x is greater than 0. So 1, 2, 7, 9, 3, 4, 5, 6, 8. Those would all also satisfy less than 10 and greater than 0. So this is considered an intersection where it takes both. It satisfies both situations. Okay, so this is an and. So it says you can graph the solutions of a compound inequality involving and by using our idea of an overlapping region. The overlapping region is called the intersection and shows the solutions, the numbers that are solutions of both inequalities. Okay, not just one or the other. So if we're going to be solving these compound inequalities that involve the word and sometimes they're actually not even going to use the word and. They're going to be written, I call it a 2-for-1. We're going to isolate our variable in the middle when we've got this 2-for-1 situation using our inverse operations on all three pieces. Okay, and then again, our shading is going to happen in the middle. Okay, ands go in. Very important to know that. I guess I can use my highlighting tool here. Okay, so here's an example of the 2-for-1. Now, when you were younger, maybe they used the words and with our compound inequalities, but now it's just going to be written as 2 in 1. Notice it says -5 is less than x plus 1, which is less than 2. So we have two inequality symbols. So now rather than doing using our inverse operations on both sides of an equation or of an inequality, we're going to do it on all three pieces. Okay, so we're going to consider dotted lines basically through all of it. Okay, so to isolate x in the middle, we'd have to move that plus 1. So notice in this example, they subtracted 1 from all three pieces and got the solution of -6 is less than x, which is less than 1. So we're locating target numbers of -6, +1, and shading in between. So looking at number 3, 8 is less than 3x minus 1, which is less than or equal to 11. So I'm going to put my dotted lines. Okay, and if I want to isolate the x in the middle, I'm going to first start by isolating the variable term in the middle. So I first want to get 3x by itself by adding 1 to all three pieces. I now have 9 is less than 3x, which is less than or equal to 12. Now to fully get x alone, we need to divide by 3 to undo that multiplication. So we divide all three pieces by 3, which gives us a solution of 3 is less than x, which is less than or equal to 4. So x needs to be greater than 3 and less than or equal to 4. So all numbers between 3 and 4, 3 is not included, but 4 will be included. Okay, so I'll put 3 here. I'll put 4 over here. Nothing special here with my counting. So open circle on 3, close circle on 4, shade in between. Okay, it's a less than. Number 4, negative 6 is less than negative 2x minus 10, which is less than 4. So again, I'm going to put my dotted lines. And if I want to isolate my variable in the middle, I need to first get the variable term alone. So that means I'm going to, not divide, I'm going to add 10 to all 3 pieces. So that gives me 4 is less than negative 2x, which is less than 14. Now I divide, and I'm going to be dividing by negative 2 on all 3 pieces. And just like all of our solving inequalities are concerned, because I'm dividing everything by a negative 2, it means I also need to flip my inequality symbols. Okay, so let's start by keeping everything in its line. So 4 divided by negative 2 gives me negative 2 is less, whoop, now I didn't even flip my sign. Negative 2 is greater than x, which is greater than negative 7. Now this is kind of backwards. We like to have our answers where our smallest number is on the left. So we're going to flip the whole entire inequality around, meaning negative 7 is our smallest number, negative 2 is our bigger number. The variable x is going to be in the middle, and it's open to the x in between the negative 7 and the x, so it's a less than now, and it's open to the negative 2 between the negative 2 and the x. So notice we're right back to less thans. Okay, so if negative 2 is greater than x, which is greater than negative 7, it means negative 7 is less than x, which is less than negative 2. So we'll go from negative 10, negative 9, negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, and 0. So we've got an open circle on both negative 7 and negative 2. And we shade in between because it is an and statement. Okay, continuing on, we've got another Venn diagram here. Circle A represents some integer solutions for x is less than 0. Circle B represents some integer solutions for x is greater than 10. The combined shaded regions represent numbers that are solutions of either x is less than 0 or x is greater than 10. It's not mathematically possible to be less than 0 and greater than 10, so that's why it has to be an or statement. So it's going to be one or the other. Okay, so we call this a union, and it's an or statement. So you can graph the solutions of a compound inequality involving or, I don't want this color anymore. I'm going to use a different color for my ors. Involving ors, using the idea of combining regions. The combined regions are called the union and show the numbers that are solutions of either of the inequalities. It's not going to be both. Okay, so if we're talking about less than 0 or greater than 10, here is our final result. Okay, and just like before, if we're going to be solving our compound inequalities with the or, we're going to be isolating our variable. And the good thing with or is the word or will always have to be there. So you're just going to have these little baby inequalities. And then our key here, when graphing solutions for or, we're shading out. Every once in a while we'll have a case where it's a very, very rare case where we'll kind of end up with an accidental overlapped region. But for the most part, ands are in, ors go out. So here is our model, okay, and we've got two completely different inequality statements that we're just solving, and then graph the solutions. So number 5, we've got 4x is less than or equal to 20, or 3x is greater than 21. So to solve the first one, I'm going to divide both sides by 4. So then I've got x is less than or equal to 5. I'm going to drag down my or. To solve 3x is greater than 21, I'm going to divide both sides by 3. And then I have x is greater than 7. So your answer does need to include that word or. So our numerical answer here is x is less than or equal to 5, or x is greater than 7. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so on the 5, we've got a closed circle and we're shading to the left. And on our 7, we've got an open circle, shade to the right. Taking a look at number 6. 2 plus r is less than 12, or r plus 5 is greater than 19. So first one, we're just subtracting 2 from both sides. So we've got r is less than 10. Got to drag down our or, that's part of our answer. Solving the second one, subtract 5 from both sides. And we've got r is greater than 14. So r is less than 10 or r is greater than 14 satisfies this particular compound inequality. So our target numbers are going to be 10 and 14 on our number line. So let's start at 8, 9, 10, 11, 12, 13. Remember, we don't want blank number lines. Okay, these target numbers are super important. So if r is less than 10 or r is greater than 14, we are in good shape. Okay, and continue to pay attention to your open versus closed circles. Notice even in number 5, we had one that was open and one that's closed. So just pay close attention to that. Okay, so here our first several examples, we actually solved these compound inequalities. And now we're going to write compound inequalities based on graphs. Okay, so reminder here, every solution of a compound inequality involving and, or that 2 for 1, those less than symbols, must be a solution of both of our inequality. And if no numbers are solutions to both, then there's no solution. Okay, the solutions of a compound inequality involving or are not always are not always two separate sets of numbers. They usually are. There may be numbers that are solutions of both parts of the compound inequality, but again, in general, our ors are just going to be going out, and you won't have to worry about any additional overlap. So if we're now kind of working backwards, we've got 4 problems here. I'm going to do 2 of them and you're going to be doing 2 of them. So first off, the big idea is we need to determine, do we have an and or an or in each? So based on the graphs themselves, I want you to tell me whether 7 is an and or an or, 8 is an and or an or, 9 and 10, whether they're ands or ors. So because number 7, we're going out, that's going to be an or. That also means number 10 is an or because we're going out. And remember, ors are 2 separate inequality statements that literally involve the word or. That then means that number 8 is an and because we are going in, ands go in. And number 9 is also an and. Okay, so we'll start with the ors. I'm going to do numbers 7 and 8, and then you'll finish up with 9 and 10. So number 7, I need the word or, so I'm going to start by writing my first inequality, which is going to be, put my variable first, my target number is -8, and it's a less than or equal to -8. Now I have my or. My second piece of my inequality, my target number is 0, so I've got an x and I've got a 0, and I've got an open circle shading to the right, so x is greater than 0. So number 7 is our first or. 2 separate inequality statements. X is less than or equal to -8, or x is greater than 0. For number 8, it's going to be an and. So remember, it's an and sandwich, meaning our variable is going to be sandwiched between our 2 target numbers. So my 2 target numbers are -2 and +5. Okay, so I've got my variable wedged in between, and I need less thans. Okay, so -2 is less than x, which is less than 5. So we don't have different symbols here. They're both less thans. Now the only factor is, do I need to put an or equal to on either one of these? Well, both of these circles are open circles, so no. Okay, so our and for this compound inequality is simply -2 is less than x, which is less than 5. So our variable is sandwiched in between -2 and 5. So using 7 and 8 as a model, complete numbers 9 and 10. Okay, so number 9 is -9 is less than x, which is less than -2. It is an and, so I need my less than symbols. It's an and sandwich. Open circles on -9 and -2, so no or equal to's. Number 10 is an or, so we write 2 separate inequalities. We both endpoints, both target numbers are closed circles. So we've got x is less than or equal to -3, or x is greater than or equal to 2.